Hi, let's practice using some of these special factoring formulas that we've learned about. We've got 8 questions here. Why don't you give them a shot, pause the video here, then come back and we'll do them together. All right, hopefully you were able to do all of them. Let's try them out together. So for this first one, 16x squared minus 72x plus 81, this is a trinomial, and notice that these values here, these are perfect squares. So I want to write this as some kind of 4x quantity squared, and I guess that'll be a minus sign. Then at the end here, we'll write 81 as a 9 squared, okay? And so the goal is we want to check to see if we factor a 2 out of this middle term, what are we going to get? Well, I guess we'll factor a negative 2 out, right? So we'll get here, what's 72 divided by 2? Well, that's going to be a 36x, okay? And so is 36x, is this equal to the product of 4x times 9, right? These two numbers here, and it is, okay? So this tells us that we're dealing with a perfect square trinomial here, and that means the formula to get this would be some 4x minus 9 quantity squared, and this must then be the factored form for this perfect square trinomial, just like that. Okay, so we're just trying to see if this is a perfect square trinomial. Let's take a look at the next one. All right, another trinomial, same idea. These look like perfect squares, so let's test this out. I'll write this as a 3y quantity squared, and at the end we'll have a 5 squared to represent 25. Now in the middle, we factor out a 2. We're left with a 15y, okay? And is 15y the product of 3y times 5? Yes, it is, okay? So in that case, this is a perfect square trinomial, and we can factor it into the form of 3y plus 5 quantity squared. That then will be the factored form. Taking a look at this one, we're going to do the exact same thing, right? These look like perfect squares to me. So I'll write this as some 2x quantity squared, and at the end here I'll write this as a 3 squared to represent the 9. And we factor a 2 out here, we're going to get a 10x, and the question is, does 10x, is that equal to the product of 2x times 3? And the answer is no, it's not, okay? 2x times 3 would be 6x. So that tells us that this is actually not a perfect square trinomial, so we can't solve it this way. This is not going to be equal to some 2x plus 3 squared, right? This would be something else. In fact, this would be a 4x squared plus a 6x plus 6x. This would be a 12x plus 9, right? And this is not what we have. Here we have a 20. Okay, so this is not going to work. We're not going to do it this way. Instead, we have to find another way to factor this, and we'll just use sort of the AC method here, right? So if we do the AC method, that's going to be 4 times 9 equals 36, okay? And so we want to find the factors of 36 that add up to give us 20, right? That's how we use the AC method here. So we can just run through this. We'll have 1 times 36, of course. Then we'll have a 2 times an 18, a 3 times a 12, a 4 times a 9, no 5, 6 times 6, and that's it, right? That's as far as we'll go, then we start repeating again. So which of these add up to give us 20? Well, it looks like it's actually going to be, this one, right? So this one here, that's going to give us 20. Now I'm just going to go through the sums here. I just want to show you the pattern. This gives us 37, this gives us 20, this gives us 15, this gives us 13, and this gives us 12. So I want you to notice that as you do this, the sums start from the highest value and then go down. Okay, it's just an interesting pattern I want to point out here. But we should be using 2 and 18. Okay, so using this AC method, let's use one of the variants. Let's use the box method. Okay, so we'll use the box method here. So we'll create our little box. And over here we'll have our 4x squared. Here we'll have our 9. And here we'll have a 2x and an 18x. Okay. Now, of course, the goal here is to take out a greatest common factor from each row and write it down here. Over here, that looks like that'll be a 2x. Over here, we can take out a 9. If we take out a greatest common factor for each column now, well, I think we can only take out a 2x here. And here we can't take anything out, so it'll just be a 1, right? And so what we're saying is that this should then equal a 2x plus 1 multiplied by a 2x plus 9. And let's FOIL this out just to double check. Of course, in the beginning, we'll get a 4x squared. The first times first, last times last will give us a 9. In the middle, though, outer times outer is going to give us an 18x, and inner times inner, that's going to give us a 2x. That does equal 20x, so yes, this does appear to be the correct factorization. So we cannot use any of those special formulas here. It's just the AC method that we've learned before. All right, let's look at this one. This is an x squared minus a 121. This looks like a difference of two squares, right? So I'm saying this is equal to some x squared minus 11 squared. And since we have it now in this form, we can write this as some x plus 11 times an x minus 11. And this will be then the factored form for this difference of two squares quadratic expression. We've got another one here, and I can also see that this is a difference of two squares. I'm going to write 144m cubed is actually 12m squared squared, right? And here I'll write this as 13n squared squared. Okay, so that's how I'm going to rewrite this. Think about it this way. And now I see this is the difference of two squares, right? So by the same formula that we did before, I will write this as some 12m squared plus 13m squared. Oh, that's an n squared multiplied by some 12m squared minus 13n squared. And that's it. That's as far as we're able to go here. We can't actually factor anything out further, right? 12 and 13 is a prime number, so there's no way to factor that out. They don't share any other common factor. So I think that's it for this one. Let's take a look at this next one here. So this is not a square here, right? So 32 is not a perfect square. And so we can't use that difference of two squares formula. Instead, we kind of have to factor this out the normal way. So I could think of this as some 8x squared plus 0x minus 32, right? That's one way I could think about that. In this case, if we were to use the AC method, well, a times c would be 8 times negative 32. If we do this in a calculator, we're going to see we're actually going to get here a negative 256. Okay, so this is AC. And so we're looking for a negative 256. We want the factors of that add up to give us 0. Okay, now this is interesting because 256 is going to have a lot of factors, right? They're going to have, of course, negative 1 and 256. You'll have a negative 2 and a, what's this going to be, a 128? Or you can keep on going. There's going to be quite a lot of factors here. And I know that 256 is actually a power of 2. It's 2 to the power of something here. Let's see what it is. So we got 2 to the first power is 2, then 4, 8, 16, 32, 64, 128, 256. Okay, so this is 2 to the power of 8. Okay, so that's the same as 2 times 2 times 2 times 2 times 4 more 2's. Okay, so this is a lot of 2's. That's what 256 is equal to. We've gotten it here in a prime factorization. So basically, if I want to think of splitting this, I guess there should be a negative sign in front of all of this, right? If I want to split this up into sort of the product of two factors, I can do it as sort of like negative 2 times all of this, right? This would be one way to split that up. Or I could write these parentheses in any way I wanted, right? I could have a negative 2 times 2 multiplied by all of this. And so by rearranging the parentheses here, we're going to basically figure out all of the possible factorizations for this negative 256. But we want the one that where the two products, the two factors, they add up to 0. That's what we want. And so actually what we want is we want the parentheses to be like this, because here now we will get this, what is 2 times 2 times 2 times 2? I believe that's going to be 2 times 2, this is 4, 4 times 4 is 16, right? So this is going to be equal to negative 16 times 16 to give us 256. When we add those together, we get 0, right? So that's the actual one we want. It'll be the last one, the last combination that we try, and that will give us 0 here. So this is what we're looking for. Okay, so just sort of a new way to think about how we can find the factors of a number. You can look at the prime factorization. That'll give you a bunch of combinations that you can try out to put together and find all of the sort of two factors that multiply to give you that number. Okay, so given that, what we actually want then is we want some kind of 8x squared, and I'm going to write this middle term as a negative 16x plus 16x minus 32, right? So I'm using this AC method here where I'm taking this 0 and I'm breaking it out into a negative 16x plus a 16x. And then from here, what we can do is recognize that addition is associative, so I can regroup however I want here. I'm going to regroup like this, and then I'm going to factor out the greatest common factor from each of these groups. And in this first one, I can factor out an 8x. So I'll factor out an 8x, and that will give me an x minus 2. And here I can factor out a 16. So a 16 will give me now here an x minus 2. And then I can factor out the x minus 2. So this will give me an 8x plus 16 multiplied by an x minus 2. So that works. But notice I can factor out a 2 from here as well. So if I factor out a 2 from here, oh, sorry, this is a 16. Okay, I can factor an 8 out from there. So this will actually be 8 times x plus 2 times x minus 2. And so this will be sort of the final form there. But notice I actually could have gotten that quite a bit faster if I wanted to. All right, let's find a way to do this a little bit faster. So let's take a copy of this, and notice I could have factored out an 8 right away. And if I did that, I would have gotten 8 times x squared minus 4. Now this is the difference of two squares. So I could have said this is equal to, let me write this, instead of a 2, I'll write this as a 2 squared. Okay, instead of a 4, that's a 2 squared. Now we get 8 times x plus 2 times x minus 2. And that's sort of a faster way that we could have done this to avoid this more complicated AC method. So if you recognize that from the beginning, good job. All right, for this next one, we have cubes. Okay, this looks like the difference of two cubes. So I'm going to write this, this 64, that's the same as 4 cubed, so 4p quantity cubed minus q cubed. Okay, that's how we do this. And you should try and remember the formula here is going to be essentially a 4p minus a q multiplied by some quadratic expression here. And let me use brackets for this. So this quadratic expression is going to give us a 4p squared. And then we're going to have a plus 4pq, and then here we'll have a plus a q squared. Okay, this should be what we get here, and I'll simplify this out. We'll get a 4p minus q, and then in here this becomes a 16p squared plus 4pq plus q squared. Okay, so this is going to be how we factor this difference of two cubes into a linear factor multiplied by a quadratic factor. Now you might ask yourself, are we done? Can we factor this any further, right? And to do this, we could try and check the AC method again, right? So here we would say that AC is equal to, well, 16 times 1, right? So that's just going to be 16. So what we want are the factors of 16 that add up to give us a 4, right? That's sort of what we're looking for here. Now the factors of 16 are going to be 1 and 16, Write that a little bit better. 1 and 16, 2 and 8, and then 4 and 4, okay? And remember what we looked at before. When you add these together, the sum is going to start from the largest to the smallest, right? We get a 17, a 10, and then an 8, right? So these sums are sort of going down like that. And so this tells us that the smallest possible sum we could get is, since this is a perfect square, it's going to be sort of this 4 plus 4 equals 8. That's as small as we get, and that's not small enough. We need a 4. So we cannot factor this any further, and this will actually be as small as we can go. That's the final factorization for this problem, okay? And that's always going to be a handy way to look at it when you're trying to factor, like, find the two factors of a perfect square. The smallest sum you can possibly get is going to be, the square root of plus the square root of that original number. Let's look at this last one now. Notice that these also look like cubes, okay? So the sum of two cubes, I'm going to try and rewrite this in terms of some 3a cubed plus some 4b cubed, okay? So we have the sum of two cubes, and the formula to factor this is we will get some 3a plus 4b, and then we're going to multiply that here by this 3a squared, and now we have a minus 3a times a 4b plus a 4b squared. And that's what this entire last term is going to be. Let us simplify it next. So we'll get, well, this is the same. Okay, so that's fine. And then in here, this will become a 9a squared. This becomes a minus 12ab and plus a 16b squared. That should be it. Now the question here is, can we factor this any further? And we could use the AC method again here, okay? So in this case, AC would equal 9 times 16. If you do the math, 9 times 16 is going to give you 144, okay? So we could try and find all the factors of 144 that add up to give us negative 12, right? So this is going to be a lot of factors though, right? There's a lot of ways that we can factor 144. We could do, 1 times 144. You could do 2 times 72. You could keep going, right? But recognize that 144 is a perfect square, right? And so at the end, the very last one we get will be a 12 times a 12, okay? And a 12 times a 12 is going to add up to give us a 24, okay? And a 24 here is too big. Okay, technically everything here should have a negative sign, right? It should be a negative sign on everything. So technically we should be getting a negative 24 here. But the idea is the absolute value here of this negative 24 is too big. We wanted a negative 12. There's no way to get this any smaller because this is the smallest sum that we'll get from the two factors of 144. That tells us we cannot factor this then. And so this then is going to be our final answer right there. Okay, so that is going to be the practice problems working with all of these special formulas. We looked at perfect square trinomials, the difference of two squares, the difference of two cubes, as well as the sum of two cubes, right? So a lot of different special formulas. Hopefully that helped out. Come back next time where we continue to look at some more interesting cases dealing with factoring polynomials. Okay, I will see you there.